Hello everybody, I am Mohammad Sadri, postdoctoral researcher at Electrical Engineering Department of TU Kaiserslautern. This is lesson number 9 of my ZYNQ training series, and this is video section 3. So section 3 of lesson 9 of ZYNQ training, and these videos, they are not official, they are my own hobby videos that I am creating at home at my free time, and the contents, I don't guarantee the correctness of all of what I say here in these videos, and I suggest you to always look at Xilinx documentation to make sure that everything is correct. By the way, I believe that with these videos you can really learn designing with Xilinx ZYNQ faster. So in the two previous sections of lesson 9, I talked about an example hardware that contains a chain of AXI stream components and then the AXI DMA, and we are going to actually program this AXI DMA using the ARM host so that it operates for us and transfer the data from the AXI stream components to the DRAM memory. So here is the hardware that we have developed in two previous sections of the video. We have the sample generator, the design of the sample generator AXI stream component I have described in detail in lesson 7. So maybe if you have not watched lesson 7, you can go back and watch lesson 7 because it contains important information that I will use right now in these videos. And then the output of these components is connected to an AXI DMA, and the AXI DMA I have talked about in previous section. In this lesson we have configured it in its simplest state, which has only one write channel, so it is writing the data to the DRAM memory, and the scatter gather engine is disabled and the read channel is also disabled. So I have the AXI DMA, then I have an AXI interconnect, and then the output of the interconnect is going to HP0 port of the ZYNQ PS. And about HP0 port I have talked in detail about in lesson 8. So maybe if you have not watched lesson 8 and you want to exactly know what does AXI HP0 mean, then you may like to go to lesson 8 and watch lesson 8 first. Okay, now for this hardware, in the previous section I went through the synthesis and then I went through the implementation, and we generated the final bit stream, and after that we came here to the file menu and exported our hardware to the Xilinx software development kit environment. And I described to you why this exporting should happen. I described that the hardware contains a lot of parameters and important information that are used during software development. These parameters are mostly related to initialization of the PS, and also the important information that I'm talking about are related to how you have configured these components that you have here. For example, what are the address ranges through which the ARM host that you have here can access different components that you have on the PL. I have described this in detail in previous videos, so I continue. I come here, export hardware to SDK, and then we want to export design 1, and we want to export to a specific location, so choose location. And again, these steps I have done before, but I will do again. And workspace, I think it will be exactly the same as the previous one. So export hardware and launch SDK. Okay, now we have the software development kit environment of ZYNQ, and actually this is the environment in which we develop bare metal applications. With the same environment, you can also develop Linux-based applications for your ZYNQ device. But I usually use it for bare metal application development. And I described to you that now that the project is created and the workspace is created, you have in fact a set of system configuration information which is reflecting different address values for different components inside your system, and the version in fact and the type of the IP block that are present in your design. So a set of information which are vital for the software development are in fact specified in the hardware platform specification, which is exported from the Vivado environment to the ZYNQ software development kit. And here we have the hardware platform 0 folder, and inside the folder we have a set of files which are all actually called, or most of them we are all beginning with the name ps7_init, ps7_init, and actually these files are all doing the same thing. So if I look at this TCL file that we have here, if it opens there, it has opened the TCL file, and if I look at this C program that I have here open here, ps7_init.c, ps7_init.tcl, practically they are exactly doing the same task. What they do, they are initializing the PS of the ZYNQ device. And what do I mean by initializing the PS? Well, I described to you in previous videos that there are a lot of important configuration information, configuration registers inside the ZYNQ PS that should be configured, that should be initialized before you can really use the PS effectively. For example, when you want to use the DRAM controller, there are a set of parameters which should be initialized before you can really effectively use the DRAM controller. So when the ARM host begins operating, the first thing it should do, it should program all of these registers. Okay, where can you find a reference to these registers? You can always use the ZYNQ ZYNQ Technical Reference Manual. The final part of the technical reference manual contains in fact detailed description of these registers. Let me show you that part for a moment. So I come one moment. This is the document UG 585, and if you look at this document, if you go at the end of the document, you find register details, and this register details is actually a very important part of this document, since it describes the configuration registers of all of the important parts related to the generally speaking the ZYNQ device. Okay, so for example, what do I have here? I have a section B6 DDR memory controller. What is inside DDR memory controller region? There are the list of registers that are related to the DRAM controller, and you can configure them, you can change the contents of them, and with the changes that you apply to these registers, the behavior of the DRAM controller will change. For example, let me DRAM parameter 0. For example, here is one of these registers. It has a set of bit fields, and each bit field is dedicated to one specific configuration behavior of the DRAM controller. Or for example, there you have, I would like to show you, for example, the parameters related to performance monitoring unit, or parameters related to AXI HP interface. So these are all parameters that are, each of them has an address, is memory mapped. You can access the register, and you can change the behavior of the design by changing the contents of the register. For example, here we have the ZYNQ PS, and as you see, the clock that we use in our hardware, the hardware that we implement on the PL, where does this clock come from? The clock comes from F clock 0 port of the ZYNQ PS. And how do you indicate the clock frequency of the clock that you have here? This is one of the configurations that you have here inside these registers. And by changing that configuration, you can change even the clock frequency of the clock which is coming outside of the PS on the fly. So up to one point the clock can operate at, for example, 50 megahertz, and then even you can change it. Or at initialization time you can specify you can select a clock frequency other than the default frequency of 50 megahertz. So these parameters are actually very important, and some of them are more important obviously, and during your development you will certainly reach some points that you need to change some of these registers, in fact through your code or manually. So I go back to the SDK environment, and what do we have here inside PS7 init.c? We have a program, a big C program, and what does it do? It indicates the contents of all of these registers. Okay, so this is actually the first program which should be executed by the ARM host. Okay, so here I have this guy, and I need kind of a code which calls the routines that we have here. We have PS7 init routine here. I need a program. I need to have a program which calls this routine that I have here and initializes, in fact, the PS, and then this program should hand the execution to the next program, to the main program that I want to write. I come here, File, New, Application Project, and I select FSBL as the name of the new application project, and the FSBL stands for First Stage Bootloader. And actually this is the program that will load this PS7 init, that will call this PS7 init, and also this is the program that, if required, will even program the PL of the ZYNQ device. I mean, it will read the bit stream from somewhere, from your SD card, and will program the PL of the ZYNQ device. And also this program is responsible for loading your main executable ELF into the memory and then passing the program counter to the location of the main executable. So maybe we describe the operation of first stage bootloader in detail later. Actually, maybe first stage bootloader needs a complete lesson for itself, and I don't want to put time right now on first stage bootloader. I think we just get familiar with its very basic and principal concepts. That is completely enough. I don't want to go to the details of this guy, because if I go into the detail it will take hours. So at first stage bootloader, it will be executed on hardware, on the first ARM core, and standalone application written in C, and just press next. And here I select ZYNQ FSBL. So from the list of templates that we have here to create projects for the ZYNQ device, actually you select ZYNQ FSBL and then you press finish. And as you do this, the entire first stage bootloader will be created for you by the Xilinx software development kit automatically. You don't need to do anything or any hand modification in the code. As it is created, it is ready to be executed on your ARM host of the ZYNQ device. So I have it here, FSBL, and here is the source of the FSBL. And actually it's a big, I would say, design, and it's very important because it's actually the first program that ARM host is executing, and it's handling very different situations. Because sometimes you are booting, for example, from the SD card, sometimes you are maybe booting over the JTAG, sometimes you are maybe booting or beginning the boot from the QPSI flash. Every time you may be doing something different, and this first stage bootloader should be executed in all of these situations. So the design of first stage bootloader should be somehow it should be sophisticated enough to handle all of these situations. So if you go through the main of this thing, you can clearly see that during the code it is talking about different situations and different cases, and for each case it performs a set of specific tasks. For example, here we have NAND boot mode, we have NOR boot mode, SD boot mode, then we have JTAG boot mode, and actually these are all the different boot modes that your ZYNQ device can have. And this program, which is supposed to be executed in all of these situations, it should be able to handle all of these cases. But for us, what we want to do at the moment is to in fact load our application to the ARM host through the JTAG, and then we want to in fact begin executing the code over the ARM host through the JTAG interface. So what I usually do for the first stage bootloader, the only thing that I usually change when I have the first stage bootloader is in fact I enable all of the debug messages of the first stage bootloader. So what I usually do, I just to enable all of the debug messages of first stage bootloader, you need this statement at the beginning of the main.c file. As you enable FSBL underline debug, then when the FSBL gets executed on the ARM host, it prints for you a set of messages that are showing what is the FSBL doing at each moment in time. And by default, when you run the FSBL on the ARM host, it is not printing any messages. So you don't understand if it is running or if it has executed successfully or not. It is not doing anything at all. It's not showing anything. It's not by default printing anything, and this is nothing. This is not something I like. So I usually always put this define FSBL underline debug in the beginning of the main.c file of the FSBL to make sure it is printing at least something, so that I can make sure it is at least being executed by the ARM host. So I have added this. And as you save, in fact, your application, you change your application and you save your application, whatever change you do here, as you save it, you can see that the development environment will compile your application again. So you don't need to, in fact, compile your application every time you change something. Here is being done automatically. And this is the code. This is the main code of the FSBL. I don't go through it. We can go through it, but as of my previous experience, if we enter this code, we will never come out. So this is just the code. It is generated an ELF for us. The ELF is actually the file which is being created for us to be executed on the ARM host. And the point is here actually very simple, and I expect you to know the point is we are running all of this application on an x86 platform, and actually the ELF, the executable file that we are creating, should be run on a ARM platform. So on an x86 platform, we are creating an application for an ARM platform. We are doing a kind of cross compilation. We are not compiling the application to be executed on the same platform. We are compiling the application to be executed on different platform. So this FSBL.elf, this is an executable file, but in the format suitable to be read and executed by ARM CPUs. In fact, the ARM CPUs that we have on the ZYNQ device. Here we have the our cross toolchain, and the cross toolchain is responsible for compiling this C code and creating for us the .elf file. And now I want to try this file. I want to see if it is working, is not working, what are the print messages, what will happen actually when I run this executable on the ZED board. So I have the ZED board here, and it's connected to my computer, and I showed you how is the connection. I will show you again. Yeah, so here is how we are connecting the ZED board to the notebook that I have here. We have actually two connections, one UART connection, which will be our console. So whatever print messages, whatever printf commands are being executed by FSBL, whatever printf you have inside the FSBL, these printfs will be transferred over this UART interface to the console that you have here on your notebook. And then on the other hand, you have the JTAG connection, and through this JTAG connection I will load the ELF file into the DRAM memory of the ZYNQ device, and then I will tell again through this JTAG memory, I will tell the ARM host here to execute this ELF. Okay, so the entire control and loading the application, they will happen here on this JTAG interface, and the UART interface I will use just as the console to see the output of my program being executed on the ARM host of the Xilinx ZYNQ device. So this is our configuration, and I come here, I come to the command line. You can always run the in fact the environment that allows you to talk to the ZED board, to the ZYNQ board through the JTAG cable from even here, the XMD console, but I really prefer to do it using the command line. So I come to the command line, and here we have our SDK environment. This is the project, this is the workspace that we have created, and I should see some ELF files here. So let's see how many ELF files are created. So let's see if we have any ELF. Yeah, we have this ELF file, and actually this is the guy whom we are going to run on the board. And on the other hand, we should have a kind of bitstream, no? Because we had this design inside Vivado, and we generated the bitstream, so I need also to have a bitstream. Where will be the bitstream? It will be inside the Vivado folder, and let me find it. Okay, so I have this bit file, and I have this ELF file, and these are the files that I need to use to program the ZYNQ device. So what I do, I go somewhere. I don't know if it's better to stay here, stay there, I don't know. The point is, here, in order to talk to the ZED board, I use the XMD, and XMD is Xilinx microprocessor debugger or Xilinx machine debugger. I don't remember which one. So with XMD, you can connect to the JTAG cable, which is connected to the ARM host of the ZYNQ device, and also connected to the PL of the ZYNQ device. And using this XMD, you can program, in fact, your ZYNQ device you can transfer the data to the DRAM memory of the ZYNQ device. You can debug your application which is being executed on the ARM host of the ZYNQ device. So it is a really capable set of commands and a really important piece of software on Xilinx toolset to debug the design and to see if the design is working correctly or not. Okay, so I turn on my board and then I make sure that all of the cables are correctly connected to the board. And the first thing you do, you run XMD, and in order to be able to run XMD, of course you should have sourced the suitable setting files. And then so I run XMD, and then the first command that you need to enter is the command through which you program the PL of your ZYNQ device. Okay, actually this is how I do it usually. It's not necessarily the first command, but I usually prefer to first program the PL. So let's do it, and in order to do that we use the FPGA command. So there's a command called FPGA inside the XMD environment through which you can in fact really program your FPGA device. So first let's find the bitstream file again, exec minus name star the bit. So here is our bit file, and what I do, I say FPGA minus F and the name of the bitstream file. So the name of the bitstream file I directly copy and paste here. Okay, now the PL is programmed. The next step that we need to do is in fact to connect to the ARM debugging system. So to do this we use the connect command, connect ARM hardware. And by this command in fact we are connected to the hardware on the ARM subsystem, which allows us to debug, to load our programs and to debug them. In fact, to get control of the CPU in hand completely. And now the next step is to load the ELF file to the memory of the ZED board. So first let's find the ELF file. Okay, this one is the ELF file that we have just created together. So I just so to load this in fact ELF file we use the DOE command. The DOE command inside the XMD is the command which is responsible for transferring the ELF into the memory of your device. Okay, and it is the DOE command. So don't worry if you don't know the details of the DOE command. They are not important. You just use the DOE command, DOE, the name of the ELF. Then DOE has a lot of options. It has a lot of possibilities, but you don't need them. You just need to use DOE with the name of the ELF. So again, if I want to go to the details of the DOE, it takes a lot of time, a very large amount of time, and it doesn't make sense, in fact, to waste time on things that are not really useful. So I just skip that. Just learn that there's the DOE command, and with the DOE command you can have the name of the ELF and it will load the ELF into the memory for you. And now if you press the run command, in fact you can run that executable on your ARM host. But the point is, before I do that, I want to in fact enable somehow the console so that I can see the output of my program being executed on the ZYNQ, on the ARM host of the ZYNQ device. In order to do that, you need a terminal program. So I have here picocom, and I use the picocom here for this purpose. So, and here is actually the command that I use for running picocom, and the point here in this command is that for the ZED board, the UART interface is recognized by the Linux kernel as TTY ACM, is not recognized as TTY USB. So here is the command. I press enter and the terminal is ready, and this is the console that I use to see the output of FSBL being executed. So okay, now I am in the XMD environment again, and I press run, and as I press run I expect to see the output on my terminal, and here is the output. So ZYNQ's first stage bootloader, release 2014.1, blah blah blah, and boot mode is JTAG. Now the FSBL.elf is executed. This means that the ZYNQ PS is right now initialized and is ready for execution of the main application or the main applications that you want to run in the next step. And the main applications, what can they be? For example, for our case, it will be the program that we will write to in fact configure the AXI DMA and to make it run. Or maybe for some developers the main program is the U-boot and then the Linux kernel. So I come back in fact to the SDK environment, and now that we have the FSBL running and our PS initialized, we go to the next step. We begin another project in which we in fact develop and we create the code that we need to program the AXI DMA, program the GPIO components, and to actually make the system working. So here I select the name of the hello world for my next application. It will be again be executing on the core 0 of the ARM host, and then I press next, and then here I select the hello world for the template of this application. Actually you can begin an empty application and create everything yourself, but I have found it more easy, for at least for this example project, to begin with hello world, and actually all of the make files, all of the necessary configurations that we need for beginning the work, they are there with the hello world, so I don't need to do them again. So I just select hello world, press finish, and here is the hello world getting compiled automatically. As you create the application, it gets compiled for you, and here I close this source, I close this FSBL, I close this hardware platform 0, and I have hello world here, and I have hello world here, and I have the in fact hello world.c, which is the main routine that is being run by the program. So right now if I go back here, I can find hello world and I can run it. So I say exec find every ELF file, and the hello world is this one, so I say DOE, and then I select this guy, and it doesn't right now contain anything. It doesn't contain any code. In fact, all of the code that the hello world contains is this simple print statement. and then later we are going to turn this code into the code that we want and we need for configuring the AXI DMA unit. So I come here and copy, paste, and yeah, something very good happened. In fact, it doesn't allow me in fact to copy the hello world.elf to the memory. Why? Because the hardware is running, the ARM cores, they are running, they are still running FSBL. In fact, the FSBL takes maybe a very small fraction of a second to be executed completely. So what is the ARM core doing right now? It's just spinning. It's not doing anything special. So in order to be able to further load applications and run new applications, just press stop, and now the processor is stopped, and then I reissue my DOE command for the hello world application. So I have a hello world here, and I have it here, and I load it, and then I run it. And now again I expect to see the hello world message on my terminal. Okay, so I see it, and now it's working. So it's time to really begin making changes and to update this code so that we can have a working design. Okay, this is it for this section of the video, and in the next section actually I continue with developing the code for the configuring AXI DMA and GPIOs, and I would like to thank Daniel Mastio, Matthias Dubon, Professor Norbert Wayne, and Professor Luca Benini for supporting me for creating these videos. And you can always find the latest material related to my videos in green-electrons.com and googlelia.com, which are both my own websites. Thanks for watching, and I will see you in the next section in which we will program the AXI DMA itself.